This question is about narrowband FM. So that's FM with a modulation index that's less than 1. So in the region of 0.1, 0.2, but generally less than. Let's write it as less than or equal to 0.5. So we're told that we can represent narrowband FM like that. So it's an expression that looks a little bit like AM or DSB with a large carrier. And the question is asking to derive an expression for the power efficiency, because you clearly have a carrier component, and here you have an upper and lower sideband. So your spectrum is going to look like an AM spectrum, where you have a carrier component and an upper and a lower sideband. So when we talk about amplitude modulation, we're interested in how much power is in the sidebands. So the question is asking for an expression. So we'd start with the expression we're given, and then try to find the power in the sidebands. So the first thing we'd do is look at this product of two sines, and then try to tease that apart, so we can turn the product into a difference. So you've got cosine of a difference term and a cosine of a sum term. So that will give us an expression where that's unchanged, but this gets split into two components. I've written sine where I should have written cosine there. Let me change that. So we've got cosine of the difference and cosine of the sum. So we clearly have a lower sideband and an upper sideband. What we want is the power efficiency, so we want the ratio of the power contained here divided by the total power here. So if we start with the carrier term, the power in the carrier term, because it's a pure sinusoid, it's simply the amplitude squared divided by 2, or the RMS value squared. And here we're assuming the amplitude is 1, so the power in the carrier is simply 1/2. Now if you look at the lower sideband, it's also a pure cosine, and the amplitude is beta over 2. The negative makes no difference to the power, so we can find the power as that squared divided by 2. So that'll give you beta squared divided by 8. And the upper sideband has the same amplitude, so it would have the same power. And these two together form the sideband power. So the lower sideband and the upper sideband combined, that's where the information is. So that is the power in the sidebands. So what we want is an expression for the power efficiency. So power efficiency is the ratio of the sideband power divided by the total power, which is the carrier power plus the sideband power. And you substitute those in, you end up with an expression like that. You can leave it like that, but it would be much neater if you simplified it by multiplying by 4, both the numerator and the denominator, so that gets rid of that fraction, and that becomes a 2. So our final expression will look like that. So that's your final expression for the power efficiency. Now, where have we seen something like this before? Remember, when dealing with AM, or DSB, the large carrier, the power efficiency looks like that, where M is the modulation index. And here beta is your modulation index. So they look identical. Now remember, we use this expression to find the upper limit for the power efficiency for AM. We said because M is at most 1, we can say that the efficiency for AM is at most 1 squared divided by 2 plus 1 squared. And that limits us to 33% for AM. So at least 67% of the power is contained in the carrier. Now, is it the same for narrowband FM? Now remember, for narrowband FM, your value for beta is not going to be that big. So beta will be less than 1. Typically, it will be less than 0.5. So in practice, your upper limit for your power efficiency for narrowband FM will be much less than 33%. So if we use a value of 0.5, you'll end up with around 11%. So much lower power efficiency. I think the criteria for narrowband FM is where beta is less than square root of 2 over 3, or something like that, and that's almost 0.5. Now that doesn't really matter. This is just to give an indication of how low the power efficiency is. What matters is this expression here, and we derived this by simply looking at this expression and finding the power of the upper and lower sidebands. And it doesn't really matter if you, so I initially wrote sine instead of cosine, and it doesn't matter if you get these signs wrong, because in the end you're only looking for the power. So I hope you found that helpful.